Good afternoon. Before I start, I would like to direct you to GitHub, where I'm having my notebook, so that while I'm doing things, maybe you can open it from there and see. There are actually two notebooks there. If I write here, does everybody see? Okay, so it's, and then it's IPPOLYTE. And there is a repository there that is called Ocean. I think it will be easy to identify. Ocean Dataset Training. There is nothing similar in there. And there's two notebooks. One has the name Copenhagen and one does not. I'm going to be using the one with the shorter name, but the longer name one, which was the original one, you cannot really run it because the file is too big, and I was not going to try it for the training session. So the objectives of this, and there was a nice overview from the presenters at the beginning of today's day, overview what can be done with DAS, what are the potential uses of DAS. And then there was some nice use cases. So I think there's already the background already set up, and there might be a little bit of an overlap. The objectives, I hope you will find interesting, even though there's not really extensive analysis here. Primarily is how to look at the content of DAS files and visualize the content of these files in different ways. There's many challenges with these files, as other presenters have said, because the files are very big, hundreds of hertz sampling rate. Do we choose, to downsample extensively? Do we spatially downsample? What do we do? And there was a lot of this decision making that was done early on and later on, and a lot of things redone, that now only a very condensed part is really presented. So for this one of the good things is that you already have seen the data that comes actually from the Geolab Fibre, and Dr. Loureiro already presented them up, but I thought it would be useful to see the relative location of this. And so the data that we're using is already processed data that comes from 10-second DAS files. The sampling rate from the date that I am using, which is the 27th of October of 2023, is at 500 hertz. It has been filtered and downsampled originally to 50 hertz. And then I already also reduced the channels, which are 11,380, downsampled that also by 10, and also removed the first few and the last few. But I needed to do further reduction because the size is again very big, and it would not work here to download. So when you go to this repository, there is SUBMERSE HCMR Jupyter notebook, and if you go to the releases to the right, let me is this okay? This is enlarged. So first, as always, let me back up again. There's two things that I have done with this data. The first phase I already explained. I further downsampled this data to 2 hertz because we're looking at oceanographic applications. So the file that you are going to be downloading that you're going to be downloading is much smaller. So first, as in all previous demonstrations, we import necessary modules. I may have a couple of extra modules than I need, but I've done so much that I... So the third cell is the important one because it will direct you to the file. It's a data.zip. So this will run. The next cell might not run, and I might have to correct something here. And it's because of the... let me see where... Yeah, the full path I have. Where is...
Data slash instead of just data.
Oh, you mean here? Hold on a second. No, I think it's, let me see where it's, I tested this before. Oh. No, I think that, let me, I'm going to find out where it is. It is the, I have to change this. I don't know where to find this. The keyboard, I'm not used to. Where is equals here? Oh, here. Okay.
No, it's just another slash after that.
I think this should do it. Yeah. Okay, let's see. Did I run this? This looks like full path. I think that's, I have the right one. Why is this not running now? Says it doesn't see it. It should see it.
Is it still in the same folder?
Yeah.
So
It shouldn't, it actually does not need this because I already used wget for that.
Yes, but it was saved in that folder.
Oh, did we do that?
Yeah. So where you change to data/data, it needs to be data/data slash.
But there is content also.
But
that it's
inside of the two data folders.
So this but that has worked. The full path is good here. It's
the file is not there.
Oh.
The file that you wrote the full path, but so the line that is commented.
Yeah.
Uncomment that one.
Okay.
It will become.
It's
data slash data.
I did this earlier to test it, and now I don't.
And another slash.
You mean this one?
Yes, and now it should run.
Okay, let's see. Oh, thank you. Okay, sorry for the delay. And so, you know, first already what you have seen is with, you know, the first thing we obviously do and others have done already is what does the content look like? And now, the original data comes in 10-second time segments at 500 hertz primarily, although there are some days that have higher sampling rate. I have written a function here that can just give you plots of different channels. I actually have converted the channel because of the downsampling to have an idea of where it is along the cable. This is 550 meters. The other one is about 5 kilometers along the fiber. Why is this important? Because the depth changes. So one of the things, once we move from one cable, let's say, to another cable, we're not familiar with this, one thing to do is to check and see what kind of records, become familiar with what is being recorded along the fiber. Especially if we're not familiar with, obviously this, we are benefited that there has been publications based on this data, but this is not always the case if you're looking at some data that not many people have looked at. And it is good to see, you know, what is the content here? Are we seeing some long periods, a lot of high frequencies? I mean, you have seen this again is at 2 hertz. So there is some things thrown out. And it gives us idea of saying, does this look right? Does it like look weird? And a lot of the stuff, the techniques that we're using are somewhat standard to techniques used when we process other types of data, like seismic data and stuff, although the data doesn't look exactly the same. So looking at spectrograms, what does the frequencies look like as time, goes by? And this is a 1 hour record. I forgot to say that this is concatenated record that was then further processed and downloaded. So at least we can see some things. We probably shouldn't be saying obviously tides because this is only 1 hour, but it will give us some idea of what kind of frequencies we have here, obviously up to 2 hertz since we threw away everything else. And for the same, again, if you see channel 10, it's not an actual channel 10, especially for Afonso, I have seen this a lot. It's actually channel 10 in the particular file, which is 10 times 50, since I picked every 50 plus an offset of 50 because I threw up the first channels because they're on land. I didn't want to see channels that are recorded, maybe things that are on the ground. I don't know that particular location, but maybe there is car traffic, maybe there's some other kind of traffic. And I thought, I don't need this. I don't need things at the end of the cable. I want to see overall what is happening here. And we do see some things here, some things this is time in minutes, let's say 12 minutes. We see some energy there that is present in most frequencies between 0 and 1, but pretty strong between, I would say, 0.2 and 0.8. And later on, probably not at a great location, I guess, within the notebook, I do have some images that I borrowed and I referenced from publications to just see overall at what kind of periods or frequencies we expect oceanic waves, oceanographic waves of different types. What are the seismology present? Where are tsunamis present, just relative to each other? Because if a lot of us are coming from interdisciplinary backgrounds and we're working with different types of waves, maybe we're interested in earthquakes, maybe we're interested in other things, maybe we're looking at some data and we're saying that there's something else going on, and we want to be able to separate. So it is good to be able to have this as a reference. So I decided, I have also plotted some spectra here, but I decided to also show a few different channels that are coming from different segments of the cable. Some of you are already pretty familiar with this because we have a part of this cable being on land. So we probably expect different things there, and we should become familiar with what is being seen there. Then we have the next segment, which is the narrow shelf, and this is where we have ocean waves dominating. Then we have a transition period going from shallow to a little bit deeper, and then we have very deep water where we probably have not much going on, but it's still good to do this for any kind of cable we have, because then we can see what to expect. Maybe if we see something, maybe we identify that something is wrong in what we did, or maybe we find something interesting. So I just put few different time series here from different, I forgot which, to place the channels here. I just have a few different ones, like at the different, representing kind of different sections of the cable, just to see. It may not even be that important in the sense that we're getting a bit of a feeling here. And we see that we have, and in the original, because I had plotted also the original data, further downsampled data, then I have been plotting and visualizing data at different stages of processing. And we obviously, in this data that I'm looking at, which is the 27th of October of 2023, we have a lot of energy in the lower frequencies, which is the stuff that we're interested in. And that was the goal, obviously, of downsampling, etc. So now another thing is stacking a lot of these things to see if we see things that are common among different channels. This is sorry, this is not the stacking. This is the average of the amplitude spectrum for all channels. One of the things that I did, again, coming from geophysics background, I was trying to familiarize myself, like, you have to make so many plots to see what is, maybe something is not so useful, but you still look at it, like, what do I see here? Do I see something interesting or not? Do I need to keep this or not? And so we move further to stacking some of the time series. We look at individual channels, okay, but what if I look at many together? This is a modified function from a tutorial of Eileen Martins, and I thought this is showing again what kind of channels are interesting. Do I need all the channels? And one of the ways to identify this, maybe one of the plots is this, because you see that there's something going on there at channels that are at the shallower part and closer to the land than others. Again, this is the channels in this file are 1127. They're downsampled by 10, so this is not in, you have to multiply by 50 to get the actual channels from the original files. So one other thing that you can try if you use this notebook, because you can use this notebook to look at things and modify things. Obviously, this is not the only thing, is you can choose, we have 1 hour duration. You can leave that because I think it's useful to keep 1 hour. And you can pick and choose. I picked minimum channel 25, maximum channel 125, because this is what I was looking at, that something is interesting is going on. These are the plots that people are looking at, where we have red and blue interchanging in the data and the strain. Again, I forgot to say that the data that I was looking at, you may have seen it in the labels, is actually nanostrain per second. So it's strain rate. And the original files were read and then further saved with simple DAS. So I made sure I save a strain rate as some of, I don't know if Dr. Loureiro described that. So that's a nice way to read quickly. There are some options, but strain, you can save it as strain, but strain rate was the one that was directly relevant to what is being recorded by the instrument. I also have done more stacking of spectra. That's another way to look at things. I don't know if this is, this is the function. So there is a function here that I have that is, again, a modified version of one from Eileen Martin's tutorial. And you have an example here on how to run it. I could probably do it here. Yeah, I guess I can do it. I don't know, does Shift Enter work in this, or let's see, did it plot? Okay, I don't see anything plotted here. Maybe because it's inside. Oh, I think it's inside. See, I'm not too familiar with Google Colab. Oh, this is the gray one. I think I commented it out because I didn't want this color. There is actually a version that shows it in different colors and you can see what is happening. This is stacking these low passed and downsampled to 2 Hz data that I have been looking at for the frequencies of interest here. So this is for all channels, but we will see another figure which is a little better in the grayscale. I'm trying different color scales here. Now, one of the things that was mentioned before, and I think everybody understands pretty clear, is that there's not that many instruments in the ocean, but we have obviously more density on land with seismometers. And seismometers are very cheap. They went from, I don't remember, like few thousand dollars back in the day to pretty much having an instrument for like few $100s. You can even make your own one. And if I understand correctly, not coming from an oceanographic background, you cannot do this in oceanography. So if we're going to be coming up with some kind of information about oceanographic waves, we don't have a direct way of coming up with, let's say, an estimate for amplitude of oceanographic waves or other information, and we have to start getting information from characteristics we can obtain from, let's say, FK spectra that others have shown in their work. So here I'm not going to, go line by line. You understand that this is a double fast Fourier transform. We're doing transformation in time and in space to be able to get a plot that can give us information about this kind of waves, read characteristics of them. Let's see, and I have an example usage here that you can run. I also have it below further down. I have a couple of functions there that you can also run and change them. So this is what is being produced if let's say you have a function from somebody else, or you write your own function for producing FK spectrum. And I have to say, looking at spectra this is not the most intuitive plot you can look at. And people sometimes reverse them in different ways. We have obviously wave number here on the y-axis and frequency on the x-axis. And the theoretical dispersion curves help a lot to kind of identify whether we have recorded waves that are dispersive. And it's something that obviously is of relevance to waves in the ocean. We can also use the landward and seaward, whether the waves are traveling towards the land or towards the sea. And this happens by looking at the different quadrantles. I don't have the lines here, although there's some faint kind of lines along the x-axis and the y-axis. So if we separate things in negative wave numbers, positive wave numbers, then we can say which one is related to landward, which one is related to seaward. And if we have symmetric, let's say, energy being recorded in different quadrantles, maybe we can say whether there is waves traveling in both directions. That would be kind of an interesting thing to observe, since I have been interested in the past with seisming phenomenon, for example, but that's in a different range of frequencies than I'm currently showing. So as I said before, and I think this might be the last thing I'm gonna talk about, or towards the last things I'm gonna talk about, is how to identify noisy channels. And people that have published work using this data or other data have used different methods to do that. And I think one kind of simpler, I guess, way to do it, maybe one simple way to do it is by looking at standard deviation. This is another way, not just by looking at the different channels and time series all together to get where we have things that are interesting in being recorded. The standard deviation can also give us some idea of where we have interesting things and do we really need to look at everything. And maybe this sounds, for DAS data, given how big the data files are, this is a really good way to work. Because I have to say that probably the majority of time I spent was the decision making of whether to throw some data out or keep it. And I didn't want to throw all the data out at the first step. I wanted to look at the different things and see whether they're useful. And given that originally I didn't have much experience with this kind of array records, I had more experience with point, recordings and stuff. I wanted to make sure, what is going to be a methodology that I'm looking at. So a lot of these things that you're looking at, and I have added the text at the README and also at the beginning of the notebook, is part of some semi-automated process that is being applied to the data before we look at. So eventually, I'm hoping that some of these things will become standardized, maybe with some modifications if we're looking obviously at a different cable, not just the Madeira. One of the benefits of using the Madeira data, we already had published work and we could compare some of this. So this has been a benefit because I don't have in situ data to compare against. So I am trying to familiarize myself by looking at things that have already been done, but again, not just fixating there, but seeing looking at my own way of doing things. What do we agree with whatever has been done already? This is the figure that I was talking to you about. Probably it should have come earlier, but I think I left it here. I didn't want to mess up the notebook too much. I made too many changes in the last couple of days to clean it up. And I do have sort of a summary of what kind of range of periods we observe different signals. Again, this is a summary. We can extract a lot of these things from the FK spectra, some of the information from the FK spectra to identify different waves present, whether they're seismic or oceanographic. But again, even though I have put everything here in a big variety of different waves, obviously oceanographic is our focus. But we cannot pick and choose what is being recorded in the data. We can only filter out the things we don't need. So I have variations of the, I have some functions here. I hope this is the one I wanted to show. Yeah. So these are just the functions that I was showing earlier. You can vary the parameters and make plots for yourself using maybe your own files and changing the numbers. This is the plot I was showing earlier that I wanted to, that shows high energy as the lighter color. And this is all the channels in this file, which is just over 1100 up to 1 Hertz. So this can be just one way to identify that there is, as we saw in other plots, there is energies in these frequencies of interest. I am going to stop here because the stuff I was playing around later on, I didn't get to a point that I thought that is useful. So I'm going to stop, but I have a couple of functions. I do have one amplitude spectrum function if you want to look at spectra individually of different channels, because again, all these different things are useful for looking at the data. And this is the first thing that we do. As Tanya said before me, we're interested in operational oceanography. So all these methodologies, even though it might look a little bit more basic, maybe than other people have presented, it is actually part of what we want to provide. So we need to have some methodology and look at meaningful ways at the content of the data and be able to convert that to things that are of interest to oceanographers. So I'm going to stop here.